Okay. Hi there. I am Nevin Lieber, and as Brian said, and LCF. I work on the SQL backend for Kokkos. I'm also on the SQL committee, Kronos, and I also on the C++ committee. I'm the vice chair of the Library Evolution Working Group Incubator. And this talk is on the Kokkos programming model, just kind of a high-level overview of what that is, and Patrick's going to dive into more hands-on and working out examples using Kokkos. And there we go. I've taken a lot of these slides. Christian runs the project from Sandia. And I've taken a lot of these slides from his and updated them. So his name is over most of these slides. So what is Kokkos? It's a C++ programming model for performance portability. Right? And our philosophy is a template library, and you have multiple different backends. We have one for CUDA, OpenMP Target, SQL, etc. And we're trying to be descriptive, not prescriptive with this. And what that means is we don't want to tell people how, what their calculations should look like. We just want to fit into, if they decide how their logic should work, we just want to fit in and make it so that it's easy to port this across multiple backends. We also follow the C++ standard closely, and we both use things from it and we contribute to it. For C++ 20, atomic ref is basically comes out of this project, and for C++ 23, we're looking to put MDSpan, which is basically a Kokkos view, into the standard. That's coming along. Hopefully it makes it in 23. And this is basically, it's a framework. It's a template library. And we want to also make things you can debug with it. You can profile all the kind of, nice things people have. It is open source. You can find it at GitHub/Kokkos. And it's gaining more and more popularity. The latest release is Kokkos 3.4. We released it, I think that's 9 days ago. 3.3 and 3.4 both require C++ 14. Some of the backends, such as SQL, require C++ 17 because SQL itself, SQL 2020 also requires C++ 17. And the major things in this release are we've done significant work on OpenMP Target and the SQL backend functionality. They're very close to feature complete. So here's kind of what the ecosystem looks like. So at the top, we have Kokkos Core. And there's two parts to that. There's parallel execution, which is really a description of where you would execute something. Is it on the host, on a device, etc. And we also have parallel data structures. Where does your data reside? And what does your data look like? Again, the host or GPU, is it, layout left, layout right? Is it strided? And we encompass all that. And on top of that, we have Kokkos kernels, linear algebra stuff that integrates well with Kokkos, and graph kernels, and tools. And then we have tools for profiling and debugging and compiler support. And right now, new stuff is basically in dotted lines. So working on auto tuning. That's a big thing we'd like to be able to do. And we also are working on remote spaces so we can have data work across multiple GPUs, multiple devices. There's also resilience. A lot of that's how can we checkpoint stuff, large calculations, you'd like to be able to stop in the middle and resume them later kind of thing. Also interoperability. We're going to interop with Fortran codes, and also we starting to work on interoperability with Python, because it's an important language for post-processing data. We have a lot of support. We have lots of documentation out there and tutorials, boot camps. There's a Slack channel. We're very responsive to it. We take support very seriously. We know that's, people get stuck, and we need to both, help them pass their problems. And if we hear the same problem, we want to be able to figure out ways to make it better in the future. The developer team. So Kokkos Core has 12 developers, 6 of which are at Sandia, and the rest are kind of spread out at the other labs. Sandia is leading the API design, though we all contribute to it. We get along well. very friendly. We take our technical decisions very seriously though. And say labs lead backend implementations. I was working on am working on the SYCL backend. And here's a list of basically the people working on it, the different various aspects. So we get into a little more detail on the two Kokkos core abstractions. As I was saying, we have data structures, and those are things like memory spaces. Like, where is the memory you're performing calculations on? GPU, CPU kind of things. We have memory layouts. Is it row major, column major? Are we tiled? Are we strided? Because we want that to all automatically work when you invoke things like parallel 4. And then traits, like how do we access the memory? Is it streaming? Are there atomic accesses, etc.? Those kinds of things. And on the other side, we have the other major abstraction is how we do execution. Like memory spaces, we have execution spaces. We have CPUs, GPUs. The executor mechanism, we are hoping executors make it as a feature in C++23 that describes where execution takes place. We want to support that. We're also the people on the committee pushing to get that in and giving our expertise towards it. There are the various patterns, right? Parallel 4, reduce, scan, and also task spawn. So you can spawn off tasks. You can basically describe the task you want to do and say go spawn, and then have a future. Say when it's done, I want to see the results of this calculation. And then how we do it. Do we have a range, or subrange would be a team? Is there a task graph? And that's all encompassed in parallel execution. And these are the two fundamental abstractions in Kokkos core, right? Data structures, where the memory is, and execution spaces, where we execute the code. And here's kind of what it looks like. So the first thing is parallel 4. Now I'm gonna like the simplest one is how number of iterations and basically the calculation you wish to perform. The only reason we need Kokkos lambda, this is a C++, this is basically a C++ lambda that captures by value. And the reason it's a macro is that on CUDA, we need to be able to say that it's both either device or host or both code. So we need a macro to be able to just put the keywords __ host __ device into the lambda. That's the only reason it's there, but these are really they are just C++ lambdas under the hood. And then we have parallel reduce. Again, range just says how we do it. And for reductions, we pass in an index and the variable we want updated. And we've optimized reductions so that we can be pretty good at them. And you can either have just a tight loop or non-tight loop. Like we can have hierarchical parallelism. You can parallel for the outside loop and one of a thread range inside, or three. And you can actually do up to 3 loops. We also have a thing called task tag. So we can, again, so I was talking about a little earlier, we can spawn off tasks. We can basically create a kind of a graph to say, here's what I want to spawn off, and then say, go do the work. And while I do other things, return future. And then the future will say, when the calculation is done, we can query it and get the results. On the other side of this coin, we have data allocation, and views take the type, and those stars don't mean pointers. In this case, we're trying to push this into C++ syntax. The stars in this case mean that we don't know this the size of those allocations until runtime. You can also use square brackets and array syntax when we do know them at file time. And the way this is changing for like MD span in C++23 would be instead of star, you would pass in a separate template parameter for each one. For star, you do standard dynamic extent, and for the static ones, you just pass in the value. I personally prefer this syntax because it's shorter. It's not as verbose, and once you get used to it, you know exactly what it means by looking at it. The other parameter is layout. Stride is left, row or column major. The memory space. Again, where is that memory? You can name memory spaces, which are good in profiling and debugging. And then just, since we said this is a two-dimensional array, that's what the star is. So we got to pass in the 2 dimensions because it's at runtime. Now, in order to transfer data between 2 memory spaces, we have deep copy. This is just mem copy across memory spaces. And it's the same order parameters as C does, right? Destination, comma, source. So this would be a deep copy of some view B into some view A. We have atomics. Here's one way to do atomic access. And as part of how we use this is how we got to pushing for atomic refs in C++ 20. Like in C++ 11, we had standard atomic type, and it turns out that's too constraining. You don't always want atomic access to everything. Like once you're done with your kernel, you may just want regular non-atomic access because you'd rather get it optimized. And so atomic refs, this is kind of like atomic ref kind of things. The operations are important, not trying to encapsulate them within a type. And finally, we have a bunch of execution spaces. We have serial threads, OpenMP, and we're working on like OpenMP target, HIP, and SQL backends as well. And there's lots more. This is just like a sampling of what we offer as part of Kokkos. And I'm going to go through an example, a gradient solver. And because there's 3 operations, we can kind of highlight how you would do this kind of thing in Kokkos. There's a vector addition, a dot product, and a sparse matrix vector multiply. So the first thing is Kokkos views. Again, so this is a single dimensional view, the size of runtime on the host. And we're saying it's unmanaged, saying we're not allocating. You can either manage or unmanaged views. And unmanaged view says we're not allocating the space, something else is keeping track of the space and will free it when it goes away, etc. And we pass in basically x in is where that space is and number of rows. And we kind of have whatever default to whatever execution space we're in. And so that's what X is. And then deep copy says, I want to copy from the unmanaged space into this new managed space. I want to copy the data no matter where it is. And now we have basically a simple data parallel loop. And this is to show off Kokkos parallel 4. I mean, most programming models have parallel 4. And so the serial version of this is just, you loop through the data and you just, assign it to Z for each index. For the Kokkos implementation, right, we said we just call parallel 4. And by the way, most of the things are really Kokkos : parallel 4. It's just on slides that just gets very noisy. These are all in the Kokkos namespace. And so you name it, pass in a number of iterations, and then pass in, it can either be a lambda, it doesn't have to be a lambda, you can do your own function objects for doing the same kind of thing. Lambdas are just simpler. And the thing I want to point out is we use parentheses here because in C and C++ we can't have, we don't have multi-dimensional support for square brackets, although we have a proposal on the table to do just that. For a lot of the people who worked on Kokkos and this kind of thing. If we get that, we'll support that syntax also. We do support that, and we do support that exact syntax with square brackets instead of parentheses for one-dimensional data. As I said, we want to be able to label things, which are good for profiling and debugging tools. And this is very simple execution policy. We just say do n iterations, and then we just pass the index. That does the calculation. And a little more complicated is dot product. And I'm going to show you how we use parallel reduce. right? The serial implementation, again, just says, go through all the data and put it all in a sum variable and then return it. In Kokkos, we want to be able to do this in parallel, so we call parallel reduce instead. And it's the same kind of thing, right? You pass in the index and you pass in, Kokkos will pass in a thread local reduction variable that things get summed into. And so these code, this code looks, very similar, right? Again, we're trying to be, descriptive, not prescriptive, right? It's the same kind of code. You just, kind of sprinkling the Kokkos parts to make Kokkos do the hard work for you. And the vector multiply, here's what the serial version looks like. So it's the serial version is, right, here's an outer loop through the rows. There's an inner loop, and then there's reduction. So it's really nested parallelism. Right, the outer loop is over the matrix rows, right? In your dot product, actually do the calculation into a reduction. And here's what it would look like, the Kokkos version. Unfortunately, it doesn't all fit on one slide with the other one. So at the outer level, you have parallel 4. And we're going to pass in a team policy because we're going to do the inner parallel 4 with a team thread range. That's over here. Again, this is just nested inside. And then inside that, parallel 4, we have nested as a parallel reduce. Here's some numbers. I don't. These are for work in progress backend, so the numbers are not crazy long because we've been focusing on functionality more than performance. But it's not too bad. And the next round for these backends, OpenMP target, and we're concentrating on performance. So another thing we offer is Kokkos kernels, which is FLAS, sparse and graph kernels on top of Kokkos. And a lot of the reason for this is because we can make the interface simpler. Kokkos view already encompasses size and stride information, so we don't have to pass that to the various functions in FLAS. So we can make things simpler, and if the interface is simpler, it's less error prone. I mean, one of the problems with FLAS is there's an awful lot of parameters there, and it's awfully easy to get things wrong. They're not differentiated by type. We also work on Kokkos Tools. Profiling, we're always working on new tools. We're very careful for the profiling stuff because we don't want to tie it to whatever's doing the display. We want to be separate. We're also, a big thing we're working on now is auto tuning. It's just a hard, it's a hard problem, but less people we want people to get sensible defaults to start with. There's a lot of knobs you can turn, but people don't know how to turn them, especially as you move to different architectures and different size problems. Debugging, we've played around with extensions to Clang to use Kokkos naming information, and also static analysis, so to have Clang tidy point out problems that you may have in your code. Our limiting factor really is manpower for a lot of these features. We're very ambitious, but we're also very limited. Our team size is decent, but if we had more people, we would do more stuff. And as I was saying about profiling and debugging, performance tuning, basically, requires insight to what your application is going to run on, and the tools are different on each platform. We just want to provide a common set of hooks that third-party tools can hook into. And the thing about it is we want to make sure there's no need to recompile, right? It uses runtime hooks, which are, if you're not actually profiling or debugging, are fairly cheap. It's basically a pointer comparison, and you should be able to set them easily. Just set up in your environment that you want to use the shared library to do those kinds of things. Here's an example of DAO, what it looks like. And again, tools can describe, we want to be tool agnostic to what's doing the profiling. Here's kind of what static analysis looks like. Basically, want to say like here, you captured a variable by reference that you shouldn't have. And we'd like to add more of those kinds of things because, especially for, things that are common, easy problems that people run into that normally we can't, it's just C++ code. We can't necessarily detect it, but Clang Tidy can. A new feature we've added is Kokkos graphs. This was in the previous release, 3.3 at the beginning of this year. Our design principle, it's like CUDA graphs, but we want make it, less foot-guns, as we say here. Reliable. So basically, you would, it looks roughly like you create a graph. You don't care what the type is, and then you add to the root saying, I want to do, okay, I have a graph, and I want to do a parallel for this function, and another parallel for of this, and then I'm ready when those two functions are completed. And then after ready is done, then I want to do a parallel reduce on those results. And then you just submit the graph and things just work. And we have some preliminary data on this. We can reuse graphs. So dash is a simple dispatch, and dash is one we're using. And so we're getting better. We're going to look at graph creation time to see if we can make that faster. And again, this is it's still early days on this stuff. This is just work in progress, and it's looking promising. Another thing we're working on are remote spaces, and that's so that we can have an abstraction across multiple devices for memory. That's scalable. Again, these are very preliminary numbers, comparing it with MPI and CUDA. And the big benefit to this is that our lines of code are it's a fifth number of lines of code to do the same kind of thing. We haven't really we're going to start working on performance for this as well. But if we want to get functionality, our philosophy is to get functionality there first and then work on performance. We have Kokkos users all over the place. And kind of here's our kind of plan for the new supercomputers. We want OpenMP kind of across the board. It's a fallback, and it's also interoperability with OpenMP libraries. But we want native things, like for instance on Aurora, we want SYCL native implementation, and ALCF we want HIP implementation. The SYCL backend, which I've been working on, we introduced it in 3.3. We're nearly feature complete as of 3.4. We don't have atomics for large types yet, so we're going to do a work graph policy, dynamic task graphs. And again, we're going to start focusing on performance. And here's just some numbers. And this graph, the parallel reduce, seems a little weird because Kokkos SYCL looks better than native SYCL. And the reason we believe is because right now, reduction support in SYCL 2020 is a brand new feature and not yet optimized. As that gets optimized, we expect those to be very similar. Also, we're going to OpenMP target backend, the HIP backend, and again, these are almost all very close to being feature complete, and we're working on performance for all of them. If you're looking for information on Kokkos, there's GitHub is probably the place to start. You can search Sandia's stuff for Kokkos. Slack, join the Slack channel. And also we have as part of during the pandemic, the Kokkos group recorded a bunch of lectures. They have 8 modules, there's 500 slides, a bunch of exercises. And again, you will, if you're working through them, come on Slack if you have questions and we'll be willing to answer them. No problem.